In this video we will discuss Sahara Desert and energy source. Whenever I visit the Sahara I am struck by how sunny and hot it is and how clear the sky can be. Aside from a few oases there is little vegetation, and most of the world's largest desert is covered with rocks, sand and sand dunes. The Saharan sun is powerful enough to provide Earth with significant solar energy. The statistics are mind-boggling. If the desert were a country, it would be fifth biggest in the world. It's larger than Brazil and slightly smaller than China and the US. Each square meter receives, on average, between 2,000 and 3,000 kilowatt-hours of solar energy per year, according to NASA estimates. Given the Sahara covers about 9 meters square kilometer, that means the total energy available, that is, if every inch of the desert soaked up every drop of the sun's energy, is more than 22 billion gigawatt-hours, GWH, a year. This is again a big number that requires some context. It means that a hypothetical solar farm that covered the entire desert would produce 2,000 times more energy than even the largest power stations in the world, which generate barely 100,000 gigawatt-hours a year. In fact, its output would be equivalent to more than 36 billion barrels of oil per day, that's around 5 barrels per person per day. In this scenario, the Sahara could potentially produce more than 7,000 times the electricity requirements of Europe, with almost no carbon emissions. What's more, the Sahara also has the advantage of being very close to Europe. The shortest distance between North Africa and Europe is just 15 kilometers at the Strait of Gibraltar. But even much further distances, across the main width of the Mediterranean, are perfectly practical. After all, the world's longest underwater power cable runs for nearly 600 kilometers between Norway and the Netherlands. Over the past decade or so, scientists, including me and my colleagues, have looked at how desert solar could meet increasing local energy demand and eventually power Europe too, and how this might work in practice. And these academic insights have been translated in serious plans. The highest profile attempt was Desertec, a project announced in 2009 that quickly acquired lots of funding from various banks and energy firms before largely collapsing when most investors pulled out 5 years later, citing high costs. Such projects are held back by a variety of political, commercial and social factors, including a lack of rapid development in the region. More recent proposals include the Two Nua project in Tunisia, which aims to power more than 2 meters European homes, or the Noor Complex solar power plant in Morocco which also aims to export energy to Europe. Two technologies. There are two practical technologies at the moment to generate solar electricity within this context: concentrated solar power, CSP, and regular photovoltaic solar panels. Each has its pros and cons. Concentrated solar power uses lenses or mirrors to focus the sun's energy in one spot, which becomes incredibly hot. This heat then generates electricity through conventional steam turbines. Some systems use molten salt to store energy, allowing electricity to also be produced at night. CSP seems to be more suitable to the Sahara due to the direct sun, lack of clouds and high temperatures which makes it more efficient. However, the lenses and mirrors could be covered by sandstorms, while the turbine and steam heating systems remain complex technologies. But the most important drawback of the technology is its use of scarce water resources. Photovoltaic solar panels instead convert the sun's energy to electricity directly using semiconductors. It is the most common type of solar power as it can be either connected to the grid or distributed for small-scale use on individual buildings. Also, it provides reasonable output in cloudy weather. But one of the drawbacks is that when the panels get too hot their efficiency drops. This isn't ideal in a part of the world where summer temperatures can easily exceed 45 degrees in the shade, and given that demand for energy for air conditioning is strongest during the hottest parts of the day. Another problem is that sandstorms could cover the panels, further reducing their efficiency. Both technologies might need some amount of water to clean the mirrors and panels depending on the weather, which also makes water an important factor to consider. Most researchers suggest integrating the two main technologies to develop a hybrid system. Just a small portion of the Sahara could produce as much energy as the entire continent of Africa does at present. As solar technology improves, things will only get cheaper and more efficient. The Sahara may be inhospitable for most plants and animals, but it could bring sustainable energy to life across North Africa, and beyond. The world's most forbidding deserts could be the best places on Earth for harvesting solar power, the most abundant and clean source of energy we have. Deserts are spacious, relatively flat, rich in silicon, the raw material for the semiconductors from which solar cells are made, and never short of sunlight. In fact, the 10 largest solar plants around the world are all located in deserts or dry regions. Researchers imagine it might be possible to transform the world's largest desert, the Sahara, into a giant solar farm, capable of meeting 4 times the world's current energy demand. Blueprints have been drawn up for projects in Tunisia and Morocco that would supply electricity for millions of households in Europe. While the black surfaces of solar panels absorb most of the sunlight that reaches them, only a fraction, around 15%, of that incoming energy gets converted to electricity. The rest is returned to the environment as heat. The panels are usually much darker than the ground they cover, so a vast expanse of solar cells will absorb a lot of additional energy and emit it as heat, affecting the climate. If these effects were only local, they might not matter in a sparsely populated and barren desert. But the scale of the installations that would be needed to make a dent in the world's fossil energy demand would be vast, covering thousands of square kilometers. Heat re-emitted from an area this size will be redistributed by the flow of air in the atmosphere, having regional and even global effects on the climate. Solar panels mean more solar radiation is absorbed and less of the sun's energy is reflected back into space. This causes the land surface to warm up. Several studies have shown this, including one which showed that the effect of warming caused by fossil fuels, via carbon emissions, was 30 times greater than the warming caused by solar photovoltaics absorbing more solar radiation. However, temperature effects may vary within the solar park and with season. In the Sahara simulation, extra rainfall happens because wind turbines represent an obstacle to free-flowing air, slowing it down and reducing the effect of the Earth spinning on airflow. This lowers the air pressure, and the difference in pressure between the Sahara and surrounding areas causes wind to flow there. When the air meets, or converges, in the Sahara it has nowhere else to go but up. As the air rises, water vapor in it condenses and raindrops form. For solar, the process is slightly different. Warmer air, heated by the panels, simply rises. However, this also promotes low pressure, causing air to flow there, converge and rise. More rainfall also means more vegetation. This increases surface roughness, as with wind turbines, and causes more solar radiation to be absorbed, as with solar panels. This reinforcing cycle is known as a climate feedback, and incorporating these vegetation feedbacks is a novel aspect of the research by Lee and colleagues. It's also hard to tell what this would mean for desertification, which is caused by poor land management, such as overgrazing, as well as by the climate. The changes to rainfall looked at in this study are regional, not global, and once the wind and solar farms were taken away, their effects would disappear and the land could revert back to its previous state. Overall, this is an interesting and important piece of research, highlighting the need to be mindful of unintended consequences, be these positive or negative, of the energy transition. Integrating these findings with other social, economic, environmental and technical considerations is essential to ensure we don't leap from the frying pan into the fire. Well, that's it for this video. I hope you enjoyed watching. If you did, let me know in the comments below, and don't forget to leave a like, subscribe, and as always, thanks for watching.